The first lesson of the grading period will cover perpendicular bisectors. To find the perpendicular bisector of a line segment, start with placing the compass at one end of the line segment. Adjust the compass to slightly longer than half the line segment length. Draw arcs above and below the line. Keep the compass the same width, and draw arcs from other end of line. Finally, place the ruler where the arcs cross, and draw the line segment. Perpendicular bisectors can be used to find the line of reflection. In fact, the perpendicular bisector is the line of reflection. The perpendicular bisectors of each preimage and image all fall on the same line. The line of reflection is the same distance from preimage and image. So as the preimage moves further away from the line of reflection, the image will further. If the preimage moves closer to the line of reflection, then the image will move closer to the line of reflection. Perpendicular bisectors can also be used to find the center of rotation. To find the center of rotation, start by finding the perpendicular bisectors of every preimage and image. Once all the perpendicular bisectors have been constructed, plot a point at their intersection, and that will be the center of rotation. The next lesson will be about transformations on the coordinate plane. Beginning with translations. First, observe that the coordinate plane is going by 2's. Next, begin translating points. The problem says to translate the triangle 15 units to the right and 12 units down. To translate this triangle, begin with picking a point, in this case B, and move it 15 units to the right and 12 units down, and do the same for all of them. Next, draw the triangle and write the coordinates of the new triangle. A prime is at -3 and -18. B prime is at -3 and 4. Lastly, C prime is at 13 and -10. Next, write the coordinate rule of the transformation. Each point has its x-coordinate added by 15 and 12 units subtracted. Using C as an example, -2 plus 15 is 13, and 2 minus 12 is -10. In fact, moving right means to add to the x-coordinate. To move to the left, subtract the x-coordinate. To move up, add the y-coordinate. And to move down, subtract the y-coordinate. a prime, is a 270-degree clockwise rotation and is at -1 and 2. B primed is a 180-degree rotation and is at -2 and -1. C prime is a 90-degree clockwise rotation and is at 1 and -2. The rule for 90-degree clockwise rotations is y, -x. The rule for 180-degree clockwise rotations is -x, -y. The rule for 270-degree clockwise rotations is -y, x. The rule for 90-degree counterclockwise rotations is -y, x. The rule for 180-degree counterclockwise rotations is -x, -y. The rule for 270-degree counterclockwise rotations is y, -x. In every reflection, the preimage and image are the same distance from the line of reflection. Point P is 15 units right from its line of reflection, which is in this case the y-axis. This means that the image, P', will be 15 units left from the line of reflection. P' will be at -15 and 20. The rule for reflection across the y-axis is -x, y. Point D is 30 units above its line of reflection, the x-axis. This means that the image, D', will be 30 units below the line of reflection, which will be at 40-30. The rule for reflection across the x-axis is x, -y. The next lesson will be over multiple isometries. This problem asks to determine the coordinates of the image of triangle JGF after going through a rotation of 90 degrees clockwise about point F and a translation 4 units down. Since the rotation is about point, the standard rotation rules cannot be applied here. The standard rotation rules are for when the origin is the center of rotation. To find the coordinates of the rotation, it may be useful to draw a circle and extend the segments of the triangle in the circle. F' will be located in the same spot as before because if a point is on the center of rotation, then the point will not be able to rotate. As for G', plot the point on the circle and move it 90 degrees clockwise. G' will be located at 6, 8. Next for J', plot the point on the circle and rotate the point 90 degrees clockwise. Once rotated, the point will be located at 2, 8. Next, begin to use the transformations. The coordinate rules for translations down by 4 is x, y minus 4. Alternatively, you can go to the graph and move F', G', and J'. When moving F' down 4 units, the new point F' will be located at 4, 2. When moving G' down 4 units, the new point G' will be located at 6, 4. When moving J' down 4 units, the new point J' will be located at 2, 4. Finish the problem by drawing the triangle. In the first problem, draw lines to move each point to 6 units to the right and 3 units down. After translating the point, to reflect a point, move at the same distance from the line of reflection. Here the line of reflection is the y-axis. Repeat this process for all the points. And once all the image points have been plotted, draw the triangle. In the second problem, reflect all points across the line y equals 1, and then across the x-axis. Start with drawing a line y equals 1, which will be 1 unit above the y-axis. Then move each point across the line the same distance it is away from the line, but in the opposite direction. Lastly, reflect each point across the axis. Make sure every point is the same distance from the axis, but in the opposite direction. Repeat for all points. Once all points have been drawn, draw the new triangle. In this problem, the triangle will be rotated 270 degrees clockwise about the origin, and then translated 4 units up. Recall the rule for a 270-degree rotation about the origin is negative y comma x. When performing the 270-degree rotation rule to h, the new point h prime will be located at -1, -1. Next, plot the point on the graph and translate the point 4 units up. The new point will locate it at -1, 3. When performing the 270-degree rotation rule to point G, the new point G prime will be located at 4, -3. Next, plot the point G prime and translate it up 4 units up. G double prime will be located at 4, 1. Lastly, when performing the 270-degree rotation rule to point J, the new point J prime will be located at 2, -5. Next, plot the point J prime and translate it up 4 units up. J double prime will be located at 2, -1. Finish the problem off by drawing the triangle. The next lesson is about corresponding parts. Corresponding parts are parts of two figures that are in the same location. In this problem, triangle ABC was reflected over the y-axis and then over the x-axis. Start by reflecting each point and drawing the second triangle. Using the second triangle, it may be easy to see that point A corresponds to N, point B corresponds to P, and point C corresponds to point L, making this triangle NPL. When naming a triangle, make sure the letters are written in the way they correspond. As for the side relationships, side AB corresponds to side NP. Side AC corresponds to side NL. Side BC corresponds to side PL. Triangle ABC is now bisected by line CF. This creates triangles ACF and BCF. Side AC corresponds to side BC. Side AF corresponds to side BF. Side CF corresponds to side CF. As for angle relationships, angle ACF corresponds to the angle BCF. Angle AFC corresponds to angle BFC. Angle CAF corresponds to angle CBF. CPCTC stands for corresponding parts of congruent triangles are congruent. In this problem, two congruent triangles. Here, use the lines to determine correspondence. So, side XJ corresponds to side HC. Side CD corresponds to side JP. Side PX corresponds to side DH. As for the angles, it may be helpful to draw arrows across in a given angle to determine which side is opposite. In this case, angle J is located across from the green highlighted line, and across the green highlighted line in the other triangle is angle C. So angle J corresponds to angle C. You can repeat this for the other angles. Angle H corresponds to angle X, and angle P corresponds to angle D. In this problem, triangles VAR and BKF are reflections. An easy way to see the corresponding parts is to line up the names in the order of the corresponding parts. So in this case, write VAR over BKF. Pointer is above F, so pointer will map to point F. V and R above B and F, so side VR will map onto side BF. A and R are above K and F, so side AR will map onto side KF. A and V are above K and B, so side AV will map onto side KB. This lesson will be about Euclid's elements, particularly about the parts of a conditional statement, how to write a conditional statement, and using counterexamples. In a conditional statement, the hypothesis starts with the word if, and the conclusion starts with the word then. So the hypothesis in this problem is the measure of an angle is 32 degrees. The conclusion in this problem is the angle is acute. This problem asks to write a conditional statement and to determine its validity. The symbols P arrow Q mean if P then Q. The conditional statement will be, if a measure of segment AB equals to 6 inches and the measure of segment BC equals to 6 inches, then segment AB is congruent to BC. Since both segments are both 6 inches, then they are congruent, so the statement is true. Counterexamples are statements made to prove that a statement is not entirely true. For an example, saying that if a polygon is a quadrilateral, then it is a square. A counterexample would be to state any quadrilateral that is not a square. For instance, trapezoids, rhombus, kites, rectangles are all quadrilaterals and not squares. As for the problem states if a number is prime, then it is an odd number. 1, 9, 15, 21. 25 are odd numbers that are not prime numbers, thus making them counterexamples to the conditional statement. This lesson will cover basics of different types of geometries. Some examples of non-Euclidean geometry are hyperbolic geometry and elliptic geometry. Each geometry depends on the surface and the type of parallel lines that can be made on that surface. Euclidean geometry uses flat surfaces, and the parallel lines remain at a constant distance from each other. Hyperbolic geometry uses a saddle-like shape, and the lines curve away from each other. And elliptic geometry uses curved surfaces, and the lines curve toward each other and eventually intersect. Another example of non-Euclidean geometry is spherical geometry. Spherical geometry is a geometry of a spherical surface. In non-Euclidean geometry, the topics like parallel lines and angles of a triangle are different. Here are some terms used in sphere geometry. A sphere is a 3D solid where all points on its surface are the same distance from the center. A great circle is a spherical line that passes through the center, making it the straightest line and the shortest distance between 2 points on the sphere. A lesser circle is a spherical segment that does not pass through the center. A spherical triangle is a triangle formed by 3 spherical lines, and antipodal points are points located directly on the opposite side of the sphere. This lesson will cover the linear pair, segment addition, and angle addition postulates. According to the linear pair postulate, if 2 angles fall on a straight line, then the angles are supplementary. Supplementary means that the angles will add to 180 degrees. In the first problem, angles ACD and BCD form a linear pair, and angle ACD equals to 120 degrees. Because they form a linear pair, then 180 degrees equals to angle ACD plus angle BCD. To find angle BCD, substitute 120 for angle ACD. This makes the equation 180 equals to 120 plus angle BCD. After solving the equation, angle BCD will equal to 60 degrees. In the second problem, angles XYZ and WYZ form a linear pair, and XYZ equals to 57 degrees. Since they form a linear pair, both angles will add to 180. The equation will be 180 equals to angle XYZ plus angle WYZ. By substitution, 180 equals to 57 plus angle WYZ, and 123 equals to angle WYZ. The segment addition postulate states, if a point is on a segment and between the endpoints, then the segment can be broken into 2 smaller segments. In the first problem, AB is 2 and BC is 4. Using AB plus BC equals AC, and then substitution, this will be 2 plus 4 equals to AC, which means AC equals to 6. In the second problem, AC is 2 and AB is 4. Using AB plus BC equals AC, and then substitution, this will be 2 plus BC equals to 10, which means BC equals 8. The last problem will be on the next page. In the last problem, AC is 6x minus 21, AB is x plus 2, and BC is 3x minus 9. Using AB plus BC equals AC, and then substitution, this will be x plus 2 plus 3x minus 9 equals to 6x minus 21. To solve the equation, start with adding like terms. So x plus 3x is 4x and 2 plus negative 9 is negative 7. Next, to solve the equation, use the inverse operations on like terms. So subtract 4x to both sides, and then add 21 to both sides to make the equation become 14 equals to 2x, and divide x and 14 by 2 to get 7 equals to x. Here are some terms associated with the angle addition postulate. The angle addition postulate states that angles that share a common vertex can be added. Bisect means to cut in half. Angle bisector is a segment that cuts an angle in half. Linear pairs are two adjacent angles on a straight line that are supplementary, therefore add to 180 degrees. Perpendicular lines are when two lines form right angles. Vertical angles, the angles formed by two intersecting straight lines. The first problem states that IH bisects angle RIX and angle GIB equals 55 degrees. Because IH bisects angle RIX, angles RIH and HIX will have the same angle measure. Angles GIB and HIX are vertical angles, so they are equal, thus angle HIX equals to 55 degrees. And since our IH and HIX are bisected angles, they have the same angle measure, meaning our IH equals to 55. Finally, by angle addition, angle RIH plus angle HIX equals to angle RIX. So 55 plus 55 equals to angle RIX, and therefore angle RIX equals to 110. The second problem asks, what is the measure of angle WAJ? Angle WAJ is the angle measure of the entire group of angles. Using the angle addition postulate, angle WAJ will equal to angle WAD plus angle DAJ. Angle WAD is congruent to angle XAJ. Angle XAJ equals to 50 degrees. Because angle WAD is congruent to angle XAJ, then angle WAD will also be 50 degrees. Lastly, angle DAJ is 85 degrees. Going back to the equation, angle WAJ equals to angle WAD plus angle DAJ will become angle WAJ equals to 50 plus 85. Therefore, angle WAJ is 135 degrees. This lesson will cover triangle congruence theorems. The four theorems of this lesson are SSS, which is side. The second theorem is side-side congruence, SAS, which is side-angle-side congruence. The third theorem is ASA, which is angle-side-angle congruence. And the fourth theorem is AAS, which is angle-angle-side congruence. Here are some examples of what the theorems look like. In the diagrams, the slashes indicate that the sides are congruent. Side-angle-side has an included angle, which is an angle between two congruent sides. Angle-side-angle has an included side, which is a side between two congruent angles. Some properties, such as a reflexive law, can be used to determine congruence. The transitive law can be used to help prove congruence. The reflexive law usually is used when the two triangles share a side. This problem asks to determine which triangle congruence theorem proves triangle ABC is congruent to triangle DCB. First, the 1/ marks indicate that side AC on ABC is congruent to side BD on DCB. Second, The two slash marks indicate that side AB on ABC is congruent to side DC on DCB. Lastly, the reflexive property states that side BC is congruent to side BC. Since both triangles have three congruent sides, this is side-side congruence. Once again, this problem asks to determine which triangle congruence theorem proves that the two triangles are congruent. Both triangles have an angle that is 65 degrees, an angle that is 70 degrees, and a side that is 10 inches. Since there are two angles and a side, this will be either angle-side angle or angle-angle side. However, because the side is not an included side, it cannot be angle-side angle. So this is only just angle-angle side congruence. The third problem asks to prove that the triangles are congruent. The triangle can be proven to be congruent by stating that each triangle has a congruent side, a congruent angle, and by using the reflexive property, they share a side WY. This triangle has two congruent sides and a congruent angle, and since the angle is an included angle, this is side angle side congruence. The fourth problem asks to determine which theorem proves the two triangles are congruent. In this problem, there is not enough information to determine congruence because you need three statements or something like a shared-sided to stated congruence. If there was another angle congruence, then may angle-angle side or angle-side angle. This lesson will cover theorems that do not prove congruence. Side-side angle do not prove congruence because two sides and an angle is not enough to prove congruence. Here is an example as to why side-side angle does not work. Both triangles have the left and right sides congruent and a 60-degree angle. However, the bottom side is bigger, thus making the triangles not congruent. Here is another example as to why side-side angle does not prove congruence. Side-side angle does not prove congruence because in a triangle, the interior angles must add to 180 degrees. Also in a triangle, the longest side must be greater than some of the two smaller sides. Here is an example of why. Three angles are not enough to prove triangles are congruent. Triangles with the same angle measures can be proportional and therefore dilations of each other. Here is an example as to why two congruent hypotenuses cannot prove congruence. If two right triangles have the same hypotenuse, it is not enough to prove congruence because right triangles can be isosceles. This lesson is about using triangle congruence theorems on the coordinate plane. The first problem asks to use the distance formula to show that the two triangles on the coordinate plane are congruent by side angle side. Although the problem asks to use the distance formula, it is faster and easier to use the horizontal and vertical changes to prove that the distance is the same. Both triangles have a side with a length of 4. Both triangles have a side with vertical and horizontal changes of 3 and 5. And both triangles have a side with a vertical and horizontal change of 5 and 7. Because the horizontal and vertical changes are equal, the triangles are congruent by side congruence. And since they are congruent, then side angle side can also be applied. In the second problem, the problem is asked to describe how to prove the given triangles are congruent by side angle side congruence. Both triangles have a side that is 4 units and another side that is 6 units. Lastly, horizontal lines are perpendicular to vertical lines. Therefore, there is an included angle between the sides. Since there are two congruent sides with an included angle in both of them, this is side-angle-side congruence. The third problem asks to describe how to prove the given triangles are congruent using the angle-side-angle congruence. Start by proving that the sides are congruent. Both triangles have a side length of 14 units. Next, use the horizontal and vertical changes to prove that the two remaining sides are congruent. Since all sides of the triangle are congruent, then all angles are congruent. So this is angle-side-angle congruence. To prove congruence using angle-side-angle, use any two adjacent angles and one included side. For an example, angles P and C, angles N and B are congruent, and sides PN and CB are congruent included sides. This lesson will be about writing a proof about the congruence of triangles. Once again, some common properties of congruence are the reflexive law, symmetry law, and the transitive law. The reflexive property is commonly used when two triangles share a side. The transitive property can be used to state that if two triangles are congruent and another triangle, then all the triangles are congruent. Recall that the midpoint of the segment is located in the middle of the segment. This problem asks to prove that angle C is congruent to angle D, given that M is the midpoint of CD and EF. The first statement is angle 1 is congruent to angle 2. This is given, as it is part of the diagram. The second statement is side CM is congruent to side DM. By the definition of the midpoint, this is true, because if M is the midpoint of CD, then M is the same distance away from C and D. The third statement is side EM is congruent to side FM. By the definition of the midpoint, this is true, because if M is the midpoint of EF, then M is the same distance away from E and F. The fourth statement is triangle CME is congruent to triangle DMF. This is true because they are congruent through side-angle-side congruence. The last statement is angle C is congruent to angle D. This is true because of CPCTC. CPCTC stands for corresponding parts of congruent triangles are congruent, and this states that if triangles have been proven to be congruent, then every corresponding aspect of them are congruent. The second problem asks to prove the triangles are congruent. The first statement says side GJ is congruent to side KM. This is true because it is given. The second statement says side HJ is congruent to side HK. This is also true because it is given. Next, because each side of triangle HJK, or the middle triangle, equal to 10, angles HJK is congruent to angle HJK. This is because if two sides in a triangle are congruent, then it is an isosceles triangle. If a triangle is isosceles, then the base angles are congruent. This triangle is also an equilateral triangle because all the sides are equal, and if a triangle is equilateral, then all the angles are the same or 60 degrees. Angle HJG is congruent to angle HKM because both are exterior angles of congruent angles. Exterior angles form linear pairs. Therefore, the angles are exterior angles to angles with the same measure, then they will have the same angle measure. Triangle HGJ is congruent to triangle HMK by side-angle-side congruence. The last statement is to say that side HG is congruent to side HM because the triangles are congruent, and since side HG corresponds to side HM, they are congruent. This is corresponding parts on congruent triangles are congruent. In this lesson, triangle congruence will be explored in a sort of what or could potentially determine the triangle congruence. The first problem asks to determine which congruence theorem proves the triangles are congruent. The first thing to note is that angles P and S are included angles. Two congruent sides with included angles is an indicator that triangle PQR is congruent to triangle STW by side angle side congruence. The second problem asks to determine which triangle theorem proves that triangle EFG and triangle HJK are congruent. Currently, there is not enough information to solve this problem. However, if triangle EFG is congruent HJK by angle side angle, then sides EF and JH are included sides. If triangle EFG is congruent HJK by angle, then sides FG is congruent to JH or sides EG is congruent to HK. The third problem asks what additional information is needed to prove that the triangles are congruent by side angle side congruence. Side angle side congruence has to have an included angle. Side FJ is congruent to HI because it is given. Side JI is congruent to JI because of the reflexive property of congruence. Because two sides on both triangles are congruent, that means that the only thing missing for side angle side congruent is the included angle, and the only place for congruent angles would be angle FJI and angle HIJ. The fourth problem asks to determine what additional information is needed to prove that triangles are congruent using angle side angle. Since triangle XYZ is isosceles side, YZ is congruent to YX, and angles YZA and YXB are congruent. Angle side angle has to have an included side. In this case, the included sides are YZ and YX. The only place for an angle to make YZ and YX included sides will be angle ZYB and XYA. The next lessons will be about circles. This lesson will go over the parts of a circle and the central angle theorem. The radius is any line segment from the center of a circle to a point on the circle. The diameter of a circle is any line segment that passes through the center of the circle with endpoints on the circle. A central angle is an angle with its vertex at the center of a circle, like angle AQC. An arc is a part of a circle, like AC. The measure of AC is the measure of the central angle formed by the endpoints. Two points on a circle determine a major arc and a minor arc. The arc with the greater measure, ACB, is the major arc. The other arc, AB, is the minor arc. A secant of a circle is a line that intersects the circle at 2 points. In this circle is a secant. A chord is a segment whose endpoints are points on a circle. In this circle, CD is a chord. An inscribed angle is an angle whose vertex is on a circle and whose sides contain chords of the circle. A tangent to a circle is a line that intersects a circle in exactly 1 point, called the point of tangency. A circumscribed angle has its 2 sides tangent to the circle. If an angle has a common vertex at the center of a circle, then the angles is a central angle and equal to the minor arc it intercepts. The major arc is 360 minus the measure of the minor arc. The measure of arc XZ is 35 degrees. By the central angle theorem, the measure of angle XYZ is 35 degrees. The major arc is 360 minus 35, so 325 degrees. The next circle has the measure of the major arc. The minor arc is 360 minus 310, so 50 degrees. By the central angle theorem, angle HIJ is also 50 degrees. The major arc is 310 degrees because it is given. This lesson is about inscribed angles, arcs, and tangents. An intercepted arc is a part of a circle that lies in the interior of an angle with endpoints that are the intersection of the sides of the angle and the circle. In this diagram, angle POD is an central angle. Angle POD is 90 degrees because it forms a linear pair with a right angle. Arc PD is an intercepted arc. By the central angle theorem, arc PD is 90 degrees. Angle PMD is an inscribed angle. Angle PMD equals to 45 degrees because the vertexes of POM form a right triangle. PO and MO are both the radius, meaning this is an isosceles right triangle making the two congruent angles as two 45-degree angles. Central angles are equal to the intercepted arc. Inscribed angles are 1/2 of the intercepted arc. If a line is tangent to a circle, then the line is perpendicular to the radius. It should be noted that perpendicular lines make right angles. The lengths of these two tangents will be equal. That is, C8 equals CB. The two tangents will subtend equal angles at the center. That is, angle COA equals angle COB. The angle between the tangents will be bisected by the line joining the exterior point in the center. That is, angle ACO equals angle BCO. The next section is about conjectures about quadrilaterals. The first section is about classifying quadrilaterals. Any four-sided polygon or shape is a quadrilateral. If a quadrilateral does not have any parallel sides and congruent adjacent sides, then it is a kite. If one of the diagonals is bisected and is perpendicular, then the kite is a right kite. If a quadrilateral has only one pair of opposite parallel sides, then the quadrilateral is a trapezoid. If a trapezoid has one pair of opposite congruent sides and opposite congruent angles, then the trapezoid is an isosceles trapezoid. However, if a trapezoid has one adjacent side that is perpendicular, then the trapezoid is a right trapezoid. If a quadrilateral has two pairs of opposite parallel sides, then the quadrilateral is a parallelogram. If a parallelogram has adjacent sides are also perpendicular, making right angles, and the parallelogram is a rectangle. However, if a parallelogram has sides that are all equal, then the parallelogram is a rhombus. If a parallelogram has adjacent perpendicular sides and all sides are also equal, then the parallelogram is a square. This problem asks to determine whether each statement is true or false. If it is false, explain why. The diagram to the right shows that a square is rectangle. Part A is true because a square is a special rectangle that has all equal sides. However, Part B is false because a rectangle can sometimes be a square. For Part C, the statement is false because parallelograms and trapezoids are not in the same family. Parallelograms always have two pairs of parallel sides, while trapezoids always have one pair of parallel sides. For Part D, the statement is false because diagonals of a trapezoid are congruent only if the trapezoid is isosceles. The main reason that this is not true is because for it to be a true statement, it must true for all cases. Part E is false Parallelograms and kites are not in the same family. Recall that kites have adjacent congruent sides and not parallel sides. Parallelograms, however, have opposite congruent sides and two pairs of opposite parallel sides. Party is true because the diagonals do bisect each other. This problem asks to identify all of the terms from the following list that apply to each figure. To classify a quadrilateral within a family, it is easier to use a diagram. When using the diagram, start with the shape that it is, and then go up to the top. In this case, the shape is a rhombus, so keep going up to the top. This means that this is a rhombus, parallelogram, and quadrilateral. This lesson will be about conjectures, about quadrilaterals. The main point will be about properties of quadrilaterals. The first quadrilateral is a parallelogram. All parallelograms have opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. Diagonals bisect each other. The second quadrilateral is a rectangle. All rectangles have opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. Diagonals bisect each other. All angles are right angles. Diagonals are congruent. The third quadrilateral is a rhombus. In every rhombus, opposite sides are parallel. Opposite sides are congruent. All sides are congruent. Two pairs of consecutive sides are congruent. Opposite angles are congruent. Diagonals bisect each other. Diagonals are perpendicular. The fourth quadrilateral is an isosceles trapezoid. Every isosceles trapezoid has only one pair of opposite sides is parallel. Only one pair of opposite sides is congruent. And the diagonals are congruent. The fifth quadrilateral is a kite. Every kite has two pairs of consecutive sides are congruent. At least one pair of opposite angles is congruent. Diagonals are perpendicular. The fifth quadrilateral is a right kite. Every right kite has two pairs of consecutive sides are congruent. At least one pair of opposite angles is congruent. Diagonals are perpendicular. Diagonals bisect each other. This lesson will be about cyclic quadrilaterals. A cyclic quadrilateral is a quadrilateral whose vertices all lie on a single circle. This problem asks to find the measure of each interior angle of quadrilateral MATH and to write the measurements in the diagram. Angle M is 100 degrees. Angle A is 118 degrees. Angle T is 80 degrees. And angle H is 62 degrees. This problem asks to find the sum of the opposite angles and to make a conjecture about the measures of opposite angles of a cyclic quadrilateral. Angle M plus angle T is 100 plus 80, which equals to 180 degrees. Angle A plus angle H is 118 plus 62, which is 180 degrees. The conjecture is that since both opposite angle sums add to 180 degrees, then in a cyclic quadrilateral, opposite angles are supplementary. The angle sum of the interior angles in a quadrilateral is 360 degrees. Every cyclic quadrilateral has 4 vertices or points that lie on the circumference or perimeter of a circle. The 4 vertices make 4 angles. In a cyclic quadrilateral, A, B, C, D, A, B, C, D are the vertices making angles angle DAB, angle ABC, angle BCD, and angle CDA. Opposite angles are supplementary, meaning that they add to 180 degrees. So angle DAB plus angle BCD equals 180 degrees, and angle ABC plus angle CDA equals 180 degrees. The exterior angle formed when any one side is extended is equal to the remote interior angle. Angle DC equals to angle DAB. This problem asks to find the measure of the fourth angle in a parallelogram given that 3 of the angle measures are 33 degrees, 147 degrees, and 33 degrees. Start with sketching and labeling the parallelogram. In a parallelogram, the angles are congruent, so the last angle is 147. Alternatively, this problem could be solved by subtracting the known angles to 360 degrees. This lesson will be about inscribing polygons. Given a segment AB, and a circle with radius AB, and a circle with radius BA. The intersection of circle A and circle B creates a triangle, but not just any triangle, but a triangle where all sides equal to the radius of the circles and therefore an equilateral triangle. To inscribe a square, create 2 radii, and use them create 2 circles. Use the radii as their radius. Plot points where the circles intersect the original circle. Then draw segments to the original points. To test whether this is actually a square, you can measure the sides to make sure that they are all equal to each other, and then the angles to make sure they are all right angles. Next is how to inscribe the hexagon. Start constructing the diameter of a circle. Then use the 2 radii to create circles with the radius being the center to the endpoints of the diameter. Next, plot points at the intersections of the new circles and the original circle. And finish the construction by drawing segments to the adjacent vertexes. To test whether this is a regular hexagon, you can measure the sides to make sure they are all equal, on that the angles all have the same angle measure. This lesson will be about angle bisectors. To create an angle bisector, construct an arc, then construct another arc at the vertexes or the intersections of the first arc and angle. Lastly, construct a ray at the intersection of the 2 arcs and the vertex of the angle. Here is a visual on how to create an angle bisector. A 45-degree angle can be constructed given a straight line. This is because a straight line is 180 degrees. So to create a 45-degree angle, you need to bisect a straight line 2 times. You can start by creating a perpendicular bisector because perpendicular bisectors bisect a straight line and form 90-degree angles. Next, start constructing an angle bisector. Start with drawing an arc or a circle from the vertex of the right angle. Then use the intersections of that arc or circle to create new circles or arcs. Finally, draw a ray using the vertex of the right angle and the intersection of the 2 new arcs. You can measure the angle to test whether this is actually a 45-degree angle. Next will be a construction of a regular octagon. Start with a construction of 2 diameters. Then plot points at the intersections. Use the endpoints of the diameter to create angle bisectors of the diameters. Once the circles or arcs are drawn, use the intersections to draw lines or rays to create the angle bisectors. Erase all circles to help see the vertexes, and finish the construction by drawing segments to each adjacent point. Once again, you can measure each side to make sure each side have equal lengths. Additionally, the angles can be measured to make sure each angle each the same angle measure. This is the end of the video. Thanks for watching.